welcome to the deep dive, where we take what you're curious about and really, we dive in.
Yeah, exactly. You send us the stuff that's got you thinking, the articles, the research paper.
And we try to unpack it. Like, what are the key takeaways? What are the connections, that maybe you wouldn't see at first glance?
Surprising connections.
Yeah, and all that without getting, too bogged down in the weeds.
Without feeling totally overwhelmed, right?
Exactly, yeah.
So today, what we're looking at is a really fascinating set of stuff that you sent our way.
Yeah, it's all about innovation coming out of MIT.
All from MIT. Lots of cool stuff.
So we're going to be diving into recent breakthroughs in quantum computing.
Quantum computing.
The absolute cutting edge of material science.
Mm-hmm.
And some advancements in how we measure things, like really precise measurement.
Precision measurement. It's incredible.
It's wild.
Yeah.
And you gave us a really great mix of sources here.
Yeah, we've got some news articles from MIT News, and then a really deep dive into a Wikipedia entry.
A Wikipedia rabbit hole.
Exactly.
But what I think is so cool about all this is these fields, which seem kind of separate at first.
Right, different disciplines.
Yeah, they're starting to talk to each other.
They're intersecting in some really interesting ways.
Yeah, which leads to those aha moments.
Big aha moments, exactly.
Okay, so one of the first things that really caught my eye was this new hub in Cambridge called the Engine Accelerator.
Oh yeah, the Engine Accelerator.
It's located at 750 Main Street.
750 Main.
And it sounds like they're building a pretty unique ecosystem there.
Yeah, what's really innovative about this place is that they're bringing together all of these incredibly advanced technologies in one location.
All under one roof.
Right. So you might have, a company working on carbon capture.
Okay.
At these crazy high temperatures, like 600 degrees Celsius.
Mm-hmm. Wow.
Right next door to a team that's working on quantum computing.
Yeah.
Right. They're chilling qubits down to almost absolute zero.
Oh, wow.
It's incredible. And this mixing, it's not just about shared resources.
Mm-hmm.
It's about creating opportunities for serendipitous collisions of ideas.
Like cross-pollination.
Exactly.
Yeah.
So you can imagine a material scientist who's working on a heat-resistant alloy.
Mm-hmm.
They might overhear a quantum computing engineer who's struggling with qubit stability.
Right.
And that kind of unexpected connection, that cross-pollination, is often where the real innovation happens.
Makes sense.
Yeah.
It's like they're designing those water cooler moments,
Mm-hmm.
but with a much higher potential for groundbreaking discoveries.
For sure.
Now, they use this term tough tech.
Tough tech, yeah.
What exactly does that mean?
So tough tech refers to these really deep technology innovations that are addressing, really big, important challenges.
Yep.
And these are the kinds of challenges that require, major breakthroughs.
Right.
In both science and engineering.
So they have a long timeline.
Exactly. A longer timeline to really mature and develop.
Yeah.
And so the engine's mission is to bridge the gap
between
the discovery, right, that happens in a university lab and an actual product that can be sold and used in the real world.
Right, to make a difference.
Exactly.
Yeah.
So it's about taking those fundamental scientific advancements and turning them into solutions.
Yeah, okay. And it sounds like they're offering a lot more than just office space.
Oh, yeah, absolutely.
The articles mentioned specialized labs, machining, and fabrication facilities.
All that, yeah.
Essentially, everything a startup needs to go from idea to prototype.
They've thought of everything.
Yeah.
So Emily Knight, she's the president of the Engine Accelerator.
Mm-hmm.
She talks a lot about how crucial this infrastructure is for these kinds of ventures, Yeah. She points out that a company can literally just start building from day one.
Because they don't have to, set all that up.
Exactly, because all the tools and spaces are already there.
Right.
And then they also have these flexible lease terms.
Which is huge for startups.
It's huge, right? Because startups, they're constantly growing and changing.
Right.
And they need that flexibility.
Right, it's grown so fast. It's incredible.
It's amazing, yeah. They've got around 100 companies there now.
Wow.
And about 1,000 people.
That's a lot
Yeah.
since just summer of 2022.
It's amazing.
Yeah, that shows a real need for this kind of support.
Absolutely. And it's not just about, the physical space.
Right.
They're also really focused on creating a community.
Okay.
So they have educational workshops, networking events.
All those things that really help. Yeah.
All those things that can be like really vital for early stage companies. You know, especially in the tough tech world, which can be really complex.
And needs a lot of money, a lot of investment.
Exactly. It's capital intensive.
Yeah.
And, you know, Knight even talks about how they want to make Massachusetts this global hub for tough tech innovation.
Wow.
You know, which would be incredible.
Yeah. I mean, that would have implications for, like, national competitiveness.
Absolutely. Absolutely.
Wow. So this isn't just like, another co-working space with a science twist.
It's way more than that.
It's a really intentional ecosystem.
It's a whole ecosystem.
With a specific goal in mind.
Yeah.
And it actually spun out of MIT in 2016 as a public benefit corporation.
Oh, that's right. Yeah.
That's an interesting structure.
Yeah, that public benefit status, it means that, there's not just focused on profits.
Right.
They also want to create societal good.
Social impact. Right.
Exactly. Exactly.
Yeah.
And, the articles talk about some of the lessons that they learned from their first location. They realized that tough tech startups, they have some very specific needs.
Right.
Like they need a lot of power. They need reinforced floors for heavy equipment.
Sure.
They need, dedicated lab space.
Makes sense.
And so a typical office building just can't accommodate that.
Right. And it sounds like they really took those lessons to heart with the renovations of this new accelerator.
It is, yeah.
They mentioned varying ceiling heights.
Yeah.
These mushroom columns, it's like they built it from scratch.
Almost, yeah. They really focused on creating flexible spaces.
Adaptable, right.
Exactly. And the amenities sound amazing.
Oh, yeah. A full machine shop.
I know, right.
Biology and chemistry labs.
Yep.
All kinds of 3D printers. They even have cold brew on tap.
Yep. That's a cinch.
For those late nights in the lab.
Absolutely.
It's like they've thought of everything.
They really have. It's all about eliminating those practical barriers.
Right. So people can focus on the science and the engineering.
Exactly. Exactly.
And they mentioned this area called the Avenue.
The Avenue, yeah.
With garage doors, which sounds really cool.
It does, yeah.
Like a flexible space for events and gatherings.
Exactly. For networking, workshops, bigger events.
Just creating those opportunities for connections.
The informal ones, yeah.
Yeah.
Which can lead to unexpected breakthroughs.
Right, right.
So cool.
And the engine accelerator, it's related to but separate from Engine Ventures, right?
Right. They're independent.
Okay.
But they share the same understanding of the challenges and opportunities of tough tech.
Right. And then MIT itself is a partner in all this.
MIT is a key partner, yeah.
Emphasizing both speed and safety as these technologies develop.
Absolutely.
Because, I mean, these are technologies that could change the world.
Potentially, yeah.
Yeah. Okay, so let's shift gears a little bit now to something that feels like straight out of science fiction. This research about direct communication between multiple quantum processors. They're connecting these modules of qubits using something called a waveguide.
A waveguide, okay.
That's pretty mind-blowing.
It is. This is a really fundamental step forward in quantum computing.
Yeah.
One of the biggest challenges in building larger, more powerful quantum computers is connecting the different processing units.
Right.
Kind of like how classical computers have multiple cores that work together. And so this research shows a way to do that using photons.
Photons.
The particles of light.
Okay, so they're using light to communicate between these quantum processors.
Exactly.
Okay, so they took these two modules, each one with 4 qubits, and they link them together using this waveguide.
The waveguide, right.
But how does the quantum information actually get from one module to the other?
So basically, the qubits act like an interface.
Okay.
They can both emit and absorb photons. And those photons travel along the waveguide.
Okay.
And what's really cool is that they can control the direction of the photon emission.
How do they do that?
Using microwave pulses.
Okay.
So they apply these really precise microwave pulses to a qubit, which excites it and makes it release a photon into the waveguide. And by adjusting the phase of the microwave pulses, they can control which way the photon goes.
Wow. So it's like a tiny little quantum laser pointer.
It's exactly like that. They can aim the light.
Amazing.
With the information to the right receiver.
And then on the other end, a qubit can, catch the photon.
Exactly. They apply a reverse sequence of microwave pulses to a qubit in the receiving module. And that makes it absorb the photon.
Okay.
And that's how the information gets transferred.
So it's all about sending and receiving these photons.
That's the key.
And that's essential for building bigger, more powerful quantum computers, right?
It's absolutely crucial. This ability to send and receive quantum information between different processors is a big deal.
It's like the foundation for the future of quantum computing.
Exactly.
Okay. Now, this next one really made me stop and think.
Okay.
Electrons exhibiting what they're calling fractional charge in graphene.
Fractional charge.
Yeah. I always thought electrons had like a single indivisible negative charge.
Yeah. I mean, that's how we usually think about them.
Yeah.
But in certain very specific situations, electrons can do some pretty strange things.
Okay.
And one of those strange things is this thing called fractional charge.
So it's like they have a fraction of their normal charge.
Exactly. It's like they're carrying a piece of an electron's charge.
Wow. And this is really rare.
Extremely rare. It's a very unusual quantum effect.
Okay. And why is this potentially important for quantum computers?
So these fractional quasiparticles, as they're called, they have this unique property.
Okay.
They're potentially much more stable.
Okay.
And less susceptible to noise.
Noise?
Yeah, like interference from the environment.
Right, which is a huge problem in quantum computing, right?
Huge problem. Building fault-tolerant quantum computers is really hard.
Right.
And these exotic states of matter, they might be a way to make more robust qubits.
Okay. So these fractional charges could lead to better qubits?
Potentially, yeah.
The article mentioned something called the fractional quantum Hall effect.
Yes, the fractional quantum Hall effect.
And it says that it usually requires these incredibly strong magnetic fields.
It does, yeah. Traditionally, to see this fractional charge, you'd need to use these huge magnets.
Wow.
Creating these super strong magnetic fields.
Like way beyond what you'd find in a normal lab.
Oh, yeah, way beyond.
Wow.
But recently, there's been a lot of excitement about seeing similar effects without those crazy magnetic fields.
Okay.
Like in some recent research on this material called molybdenum ditelluride.
Molybdenum ditelluride.
Mm-hmm.
Okay. So what's happening in this fractional quantum Hall effect?
So in this effect, the magnetic field forces the electrons into these very specific orbits.
Okay.
And these orbits, they behave collectively as if they have a fraction of the electron's charge.
Okay. So it's like the whole system is acting like it has these fractional charges.
Exactly.
Okay.
And now, a team at MIT, they've seen signs of this anomalous fractional charge in graphene.
In graphene?
Yeah. And they've done it with just 5 layers of graphene.
5 layers? That's like incredibly thin.
It's incredibly thin, yeah. Just a few atoms thick.
Wow.
It's pretty remarkable.
Okay. How did they do it?
So graphene is already known for having some really strange electronic properties.
Mm-hmm. Mm-hmm.
And this discovery just adds another layer of weirdness.
So they were studying electrons in this 5-layer graphene, and they cooled it down to like almost absolute zero.
To ultra low temperatures, yeah.
Wow.
They used a brand new dilution refrigerator.
Okay.
To get it really, really cold.
And why do they have to make it so cold?
Well, when you cool things down that much, the electrons slow way down. And that allows them to interact in these subtle ways that you just don't see at higher temperatures.
So they're looking for these interactions that only happen at these super low temperatures.
Exactly.
Okay. And then they applied an electrical current to this super cooled graphene.
Mm-hmm.
And they measured the voltage.
That's right. And what they found was really interesting.
Okay.
The voltage they measured was equal to the current multiplied by a fractional number.
A fractional number?
Yeah. Along with some fundamental constants of physics.
Yeah.
And so the researchers, Professors Liu and Han, they were pretty surprised at first.
Yeah, I bet.
They said they didn't even recognize it right away.
What, they didn't recognize that they had found fractional charge?
Yeah. It took them a minute to realize what they were seeing.
Wow. What a moment that must have been.
Incredible.
And this is the first time anyone has seen this in graphene, right?
First time ever.
That's a big deal.
Huge deal.
Yeah. And Professor Zhu, who led the research, he mentioned another possibility. Oh, okay.
That graphene can also be a superconductor.
That's right. Under the right conditions.
So imagine having fractional charge and superconductivity.
In the same material.
Together.
It's mind-blowing.
That would be wild.
It would open up all sorts of possibilities for new quantum devices.
Yeah.
And their team, they're continuing to investigate.
To see if they can find other weird electronic states in graphene.
Exactly. Who knows what else they might discover.
Okay. This next one is a little bit more abstract.
Okay.
but it's still incredibly fascinating.
I'm intrigued.
It's the first ever measurement of the quantum geometry of electrons.
Quantum geometry.
Yeah.
Okay.
I understand we can measure, like, their energy and their velocity, but shape at the quantum level?
That's a new one. That's wild.
Yeah, it's a really strange concept.
Yeah.
Up until now, it's been mostly theoretical.
Okay.
So we've been able to see how electrons move in a material and what energy levels they occupy.
Yeah.
But understanding the geometry of their wave function.
Wave function.
Yeah, which basically describe the probability of finding an electron in a certain spot.
Okay.
That's been much harder to measure.
Okay, so the wave function describes where the electron is likely to be.
Exactly. It's like a map of possibilities.
Okay.
And the geometry of that wave function, well, that's been really tough to get at until now.
Okay. And they use this analogy in the article.
Oh, right.
Of a ball versus a Mobius strip.
Yeah, to illustrate different kinds of wave functions.
Can you explain that a little bit?
Sure. So imagine a simple electron wave function.
Okay.
It's kind of like a smooth, featureless sphere.
Okay, like a ball.
Exactly. It's uniform, no twists or turns.
Okay.
And that's what we call a trivial wave function.
Trivial. Okay.
Now imagine a Mobius strip.
Okay.
It has that single twist, right?
Right.
And if you trace your finger along it, you'll end up on the opposite side.
Yeah.
That's like a non-trivial wave function.
Non-trivial.
It's more complex. It has these twists and turns.
Okay.
And a lot of the exciting new materials that researchers are working on, they have electrons with these non-trivial wave functions.
So these non-trivial wave functions are what make these materials so interesting.
Exactly.
Okay. But why is it so important to be able to measure this quantum geometry?
Well, as we discover more and more of these new materials, we need to understand how they work.
Right.
At the most fundamental level.
Yeah.
And the quantum geometry, that's part of the blueprint.
Okay.
It tells us how the electrons are behaving.
And that determines the material's properties.
Exactly. So, like, its electrical conductivity, its magnetic properties, all of that is influenced by the quantum geometry.
So if we can understand the geometry, we can potentially control these properties.
Exactly. And that's key for designing new and better devices.
Wow. And it's funny, the COVID-19 pandemic actually played a role in this research.
Oh, really?
Yeah. One of the researchers, Professor Komen, he ended up running some of the experiments by himself.
By himself?
Yeah, in Italy.
Oh, wow.
Because of travel restrictions.
That's wild.
Yeah. Professor Kang, who was in South Korea, couldn't travel to Italy.
Right.
So Komen stepped in.
That's pretty amazing.
Yeah. He even said it might be one of the last times he actually gets to, like, run experiments himself.
Oh, wow.
Yeah, because his role as a professor is more about leading and supervising now.
Right. Guiding the next generation of researchers.
Yeah.
That's how it goes.
Okay. Now, to get a better grasp of the basics of all this quantum stuff, let's turn to the Wikipedia entry on quantum computing.
Wikipedia, our trusty guide.
For someone who's, like, trying to wrap their head around this field, what are the absolute key things they need to understand?
Okay. So the most fundamental thing is this. A quantum computer uses the rules of quantum mechanics.
Okay.
To do calculations.
Okay.
And those rules are very different from the rules of classical physics.
Right.
And that's where the power comes from.
Okay. So classical computers, they use bits, right?
Like bits, which can be either 0 or 1.
0 or 1. But quantum computers, they use qubits.
Qubits.
And what's so special about qubits?
Well, qubits can be in a superposition.
Superposition.
Which means they can be both 0 and 1 at the same time.
Whoa. That's like mind-bending.
It is. It's one of the things that makes quantum mechanics so strange and so powerful.
Okay. And classical physics just can't explain how that works, right?
Nope, it breaks down completely.
Okay. And this superposition, this ability for a qubit to be in multiple states at the same time, that's what gives quantum computers the potential for that exponential speed up.
That's right.
That we always hear about.
For certain calculations.
Right.
So for certain problems, a quantum computer could be way, way faster than even the most powerful supercomputer.
Like unimaginably faster.
Exactly.
For like specific tasks.
For specific tasks.
Like what kind of tasks?
Well, breaking encryption.
All right.
Simulating molecules.
Simulating like how molecules behave.
Yeah, at the atomic level.
Okay.
These are problems that are just too hard for classical computers.
Right. Even the best ones we have today.
Even the best ones.
And this idea of a quantum computer doing something that's just impossible for a classical computer in a reasonable amount of time.
Right.
That's quantum supremacy, right?
Yeah, or quantum advantage.
Quantum advantage.
Which is a term that's becoming more common as the field progresses.
Okay. So this speed up, it comes from the fact that qubits can explore so many possibilities at once.
That's right. It's called quantum parallelism.
Quantum parallelism. Okay.
It's like they're doing many calculations simultaneously.
Wow.
Which is something classical computers just can't do.
Okay, the Wikipedia entry mentions some early quantum algorithms.
Oh, what?
That maybe didn't solve, like, really practical problems.
Right.
But they were important for showing what quantum computing could do.
Yeah, they were like proofs of concept.
Okay.
Showing that quantum computers could actually work.
Like, in principle.
In principle, yeah.
Okay. And they mentioned the Deutsch algorithm.
The Deutsch algorithm, yep.
The Bernstein-Bazarani algorithm. And Simon's algorithm.
That's right.
What did those algorithms do?
So those algorithms, they prove mathematically that by using superposition, a quantum computer could gain information or solve certain types of problems much, much more efficiently than any classical algorithm could.
Wow.
So they were really important for establishing the theoretical foundations of the field.
Okay. And then in 1994, along came Peter Shor.
Peter Shor.
With his famous algorithm.
Shor's algorithm.
Which really put quantum computing on the map.
It did, yeah.
Because of its potential to break RSA encryption.
RSA encryption.
Which is like the backbone of online security.
That's right. A lot of our digital world relies on it.
So what did Shor's algorithm do?
So Shor's algorithm showed that if you had a powerful enough quantum computer, you could factor very large numbers, exponentially faster than any classical computer.
Okay.
And that's a big deal because the security of RSA encryption, it relies on the fact that it's really, really hard to factor those large numbers.
Right.
So Shor's algorithm basically said, hey, quantum computers might be able to crack the code.
Wow.
And that got people really excited.
And worried a bit.
Yeah, definitely a little worried too.
Yeah. And then shortly after, Love Grover developed his algorithm.
Grover's algorithm.
Which is for searching.
Searching unsorted databases.
And that's a really common task, right?
So common, yeah.
And his algorithm provides a quadratic speedup.
Quadratic, yeah.
So it's not as dramatic as an exponential speedup.
True.
But it's still significant.
Oh, yeah, absolutely.
And around the same time, Seth Lloyd made some big contributions.
Seth Lloyd.
Showing that quantum computers could simulate other quantum systems.
Right.
Which Richard Feynman had predicted.
Yeah, Feynman had this idea a while back.
Yeah. Okay, so let's talk about the qubit for a minute.
Okay.
The qubit is the basic unit of quantum information.
The building block.
Yeah. It's a two-state quantum system.
Right.
But it's not just a simple 0 or 1, like a bit, right?
It's way more than that.
Okay.
So mathematically, you can describe the state of a qubit as a combination of two basic states, which we call 0 and 1.
Okay.
But we write them with these special brackets.
Right.
Like 0 with a little bracket around it.
Right. Dirac notation.
Yeah, Dirac notation.
Yeah.